I have something to say. You have all been building HHO generators wrong. Well, at least some of you. Stick around and I'll explain why. So if you spent any length of time on YouTube, you're probably familiar with the whole HHO thing, even if you don't frequent the engineering and tinkering sphere. It's a fun and easy way to make loud explosions that trigger your neighbor's World War II PTSD, and a lot of people claim it's some sort of free energy device that makes your car run on water. And while you could use solar or wind to perform water electrolysis to make hydrogen that a car engine would run on with some minor modifications, it's not some sort of magic cheat to the laws of thermodynamics. Those claims typically come from that same side of YouTube where you find videos about healing crystals or anti-gravity devices, and for whatever reason they're always recorded on a flip phone at 144p. An HHO generator is just an alkaline water electrolysis cell where the gases aren't separated, meaning you get a perfectly stoichiometric mixture of hydrogen and oxygen. And I know what you're thinking, wow, isn't that super explosive? And the answer is yes, it is. One tiny bit of static electricity or even a mouse farting and this mixture will detonate with a velocity as high as 3,000 meters per second. But because the density of the mixture is so low, when the detonation happens, it doesn't really do much if it's unconfined, so the only damage is likely to be your hearing. Despite its volatility, this stuff actually does have a use, mainly as welding gas because the mixture burns at about 2800 C. It was actually used briefly in the late 1800s and early 1900s before acetylene came along, which can burn as hot as 3300 C. It's still used in some small-scale applications because it's really convenient to produce what's essentially a tiny welding flame without having to go and constantly top off gas cylinders at the store. In theory, it's really simple. You just stick a bunch of plates in a solution of water and electrolyte like baking soda or sodium hydroxide, apply some voltage, and then start making gas. But like with anything in life, there's some caveats. First of all, your electrode plates are going to get eaten alive by this process if you don't choose the right materials. Graphite is chemically inert, but it'll erode, so platinum is really the best thing, but it's cost prohibitive, so my material of choice has always been stainless steel. Specifically, you need the 316 alloy of stainless steel, which is not the stuff you typically get at the store. The most common stainless alloy is something called 18-8 or 304, which may be fine for doorknobs on your house or on the trim of your car, but won't hold up very long in the alkaline electrolysis environment. Here's an example of what happens to 304 stainless after just a few hours of electrolysis in a 10% potassium hydroxide solution with around 100 milliamps per square centimeter. The plates are pretty messed up and there's some sort of cancerous chromium goo left behind that I really don't want to touch. So yeah, definitely use 316 stainless. It costs more, but it actually stands up to chemical attack. The other caveat is the electrolyte. There's lots of different compounds that can be made with electrolysis, but if you're doing it specifically for hydrogen or oxygen production, you want alkaline water electrolysis, meaning you're going to use either baking soda, sodium hydroxide, or potassium hydroxide as your electrolyte. A lot of people prefer to use baking soda because it's pretty safe and non-toxic, but the problem is it gives off CO2 during electrolysis and eventually transforms into sodium hydroxide. Having that CO2 in the mix is going to reduce the flame temperature. So you really just want to use either sodium or potassium hydroxide. Now people will argue about which one is better, but the reality is they're really not that different and sodium hydroxide is a lot cheaper, so that's what I use. I typically use around 10 to 20% sodium hydroxide. Past 20%, the conductivity of the solution will actually start to go down, but if you're worried about dissolving your skin off in an accidental spill, even a few percent is enough to make the solution pretty conductive without being too dangerous. Now, perhaps the most important caveat is cell geometry and voltage. In theory, water splits at 1.23 volts, but with a 20% sodium hydroxide solution, I found the threshold voltage to be about 2 volts even. With a typical resistive load, current is voltage over resistance, but in the case of an electrolysis cell, it's voltage minus threshold voltage over resistance. For this reason, you can't just measure the resistance of a cell with a multimeter because the low voltage test signal it produces isn't enough to overcome the voltage threshold for electrolysis. You have to actually measure current at several points over the threshold voltage, and the slope of that line on a graph is the resistance of the cell. To calculate the resistance of a cell when I was making my design, I used this online table, which I've linked in the description. It only goes up to 5% sodium hydroxide, which is about 200 millisiemens per centimeter. But from tests, I know that it's around 400 millisiemens per centimeter at 20% concentration. Siemens are a unit of conductivity, meaning the inverse of resistivity. So for example, with the design I'm going to build in this video, my exposed plate area is 53 square centimeters with a gap of 4 millimeters, which gives 133 centimeters. Multiplying that by the conductivity of a solution gives a value of 53, so about 0.019 ohms or 19 milliohms. That means if I want to run 10 amps through a cell with a threshold voltage of 2 volts, I need a total voltage of approximately 2.2 volts. At 2.2 volts, the reaction would be about 56% efficient conversion of electricity to hydrogen and oxygen. More voltage would increase the current draw of the cell and the production rate of gas, but it would also reduce the efficiency because out of the current that's going in, only 1.23 volts of it is going into electrolysis and the remainder is going into heat. There's also a maximum current density because as the production rate for a cell goes up, there's so many gas bubbles forming that they actually create non-conductive voids in the electrolyte and increase its resistance. This is why if you apply a relatively large voltage to a cell, you'll momentarily see a very high current, but over several seconds it will drop as more bubbles are produced until it settles into equilibrium. So rather than increasing the voltage on an individual cell, the energy efficient thing to do is to have multiple cells in series. So if you put 2 of these example cells in series at 4.4 volts, you're still pushing 10 amps, but the efficiency is the same and the gas output is doubled. On the flip side, 4.4 volts across a single cell could theoretically give as much as 126 amps, but the efficiency would be just 28% and you would overheat extremely fast. If you just kept cranking up the voltage like this, all you'd have is a water boiler that spits out hydrogen and oxygen as a byproduct. There's also the issue of logistics. It's easy to find power supplies that are 40, 50, even 100 volts with 10 to 15 amps of output, but it's a lot harder to find power supplies that can put out several hundred amps at a few volts. The few supplies that can do it are probably much more expensive per watt too. So the most practical solution to a high-output HHO generator is to have as many cells as possible, but using a relatively moderate current, like 10 or 15 amps. In my case, the plan is to have 20 cells at 10 amps being fed by a 48-volt supply, meaning each cell would be at 2.4 volts. So the obvious solution is to have a big stack of plates separated by gaskets, which is exactly what a so-called dry cell is. The problem is, every single time I've tried to build one of these, they eventually leak no matter how much effort I put into sealing them. So the alternative is to put the entire plate stack in the electrolyte as one piece, a so-called wet cell. But this is actually a terrible design, which is why I said at the beginning of the video that people are building HHO cells wrong. I was referring specifically to so-called wet cells. If all your cells are physically separate, the voltage of your power supply would be evenly divided between the cells and they'd all be producing the same amount of gas. But when you just shove the whole plate stack in an electrolyte bath and turn on the power, that's not what happens. This is because the current has the option to simply bypass the inner cells rather than passing through them. If the resistive voltage across the section of electrolyte is less than the 2 to 2.5 volt drop across this cell, it's just going to bypass it altogether, so the only plates that are actually producing any gas are the very outer ones. Here's a small example with 6 cells that have a large amount of space on either side that current could flow through. At 11.4 volts, we've got a whole 10 amps, but look at the gas production. It's only on the outer plates and none of the inner cells are producing anything. If I measure each cell individually, we can see the problem. On the outer cells, we've got a voltage drop of around 2.5 volts, but on the inner cells, they're all far below the threshold for electrolysis because the current is just going around them. As it currently stands, this stack is just generating mostly heat. Now let's see what happens if I put barriers between the cells. Now these barriers aren't sealed, so a little bit of current can bypass each cell, but it's a small enough amount that it's not a huge problem. When I apply a few volts, we can see at first there's a small amount of gas generation on the outer cells from that small amount of leakage current, but as I crank the voltage up, it evens out, and just by observing the bubbles, we can see that all 6 cells are producing approximately the same amount of gas. The difference in output is really clear if we compare the cell voltages to the previous configuration. At really low voltages, there's some imbalance due to the leakage current, but once we crank it up a little bit, it more or less evens out. If the cells were physically separated, this would pretty much be a perfectly flat line, assuming the geometry of each cell was identical, but this is close enough to work fine, I think. So here's my design. It's a case that holds 21 2x6-inch stainless steel plates for a total of 20 cells. The edges have 7 millimeters covered on either side to act as a sort of collar to minimize the bypass current without totally physically separating the cells. This reduces the available plate area, but at my goal of 10 amps, it should still be under 200 milliamps per square centimeter, which is a pretty reasonable current density. I start with these 2x12-inch plates and cut them in half by hand with a hacksaw, leaving the clean edges at the bottom of the casing and the messy edges sticking out the top slightly where it doesn't matter so much. The enclosure will be a casing for a water filter. There's a lot of unused space inside that'll be filled with extra electrolyte, but the reason I chose this is because I wanted to build up 5 to 10 psi of pressure to operate the torch, and the casing has 2 O-rings which will seal the whole thing under pressure. To connect the leads to the cells, I cut narrow slots in the casing cap, ran 1-inch strips of stainless through, and then sealed the gap with silicone caulk. Then I did a pressure test with compressed air, and we do have a little bit of gas escaping, so I guess I'll have to add some more sealant. The terminal lugs are just some 1/4-inch copper tubes crushed onto my wires because I'm too lazy to go and get proper crimp terminals. Once that's done, I fill up the casing with distilled water and add the sodium hydroxide electrolyte. I'm adding enough to make a 10% solution, which should provide more than enough conductivity to hit my 10 amp target at 48 volts. A printed standoff is added to the bottom of the casing, and the purpose of this is just to make sure the cell bottoms out at a known depth so I know where it'll end up with respect to the water line since I can't see inside the thing when it's closed up. Here's a graph of current versus voltage. If the cells were perfectly separated, we'd have zero current until we hit around 40 volts, which is about 2 volts per cell. But because of bypass current I mentioned earlier, we get a little bit of current before all the cells start electrolysis. And there's some gas production. So far so good. Here you can see the pressure inside the cell rising when I hold my thumb over the output tube. The bubbler is just a smaller, clear water filter casing that has a 3D printed adapter glued into the inlet port with a silicone tube that goes down to the bottom of the casing. This one also uses a 1/4-inch barb fitting sealed on to the larger PVC threaded plugs. To test the flow rate, I got an empty plastic bottle and measured its volume, 1.92 liters. The plastic bottle is completely filled with water and placed upside down in a much larger bucket, which is also filled with water. I flow gas from the output tube up into the plastic bottle and measure the time it takes to fill. I should point out that this is super dangerous because at the end of the test we'll have almost 2 liters of this explosive gas. Fragmentation risk isn't very high, but hearing damage is a real risk if this goes off, so I make sure to wear eye and ear protection here. I also ground myself and make sure there's no ignition sources nearby. Anyway, once we get bubbling outside of the bottle, that means it's completely filled with gas and the water has been completely displaced from it. At 43 volts and 4.4 amps, it took 2 minutes and 48 seconds to fill the bottle, and at 45.5 volts and 9.5 amps, it took 1 minute and 15 seconds to fill. Working out the chemical energy versus the input power and time, that comes out to 48.2% and 47.2% efficiency, respectively. This is actually pretty good because theoretical efficiency is 57% and 54% respectively, and we're not too far off from those numbers, so we're getting almost all the gas we possibly can given the input power. Just an interesting side note, when the bottle is completely full, you can see it's somewhat opaque, and this is just a mist of superfine sodium hydroxide particles. The sodium residue is the reason the torch flame will come out bright orange. If it's totally pure, the flame is actually invisible. Now for the torch. For the first iteration, I used an M6 threaded brass adapter because it can either fit a MIG welding tip or a 3D printer nozzle, both of which come in various diameters below 1 millimeter, so I can thread in different ones to see which works best. The threaded adapter is braced to a 1/4-inch copper tube, which came out really messy because I didn't have flux, but it did seal when I tested it under pressure. At around 10 amps using a 0.4 millimeter nozzle, we're getting just under 4 psi of pressure to the torch. The gas is moving fast enough to blow the sand out of the way. Seems like it's too fast to ignite a stable flame though. So I switched it to a 0.8 millimeter nozzle, and that seemed to work pretty well. Donald Trump is deporting trans people by launching them into the sun. Gavin Newsom is giving free mansions in Beverly Hills to MS-13. We have 2 weeks to act on climate change before the Cheesecake Factory is underwater. And this is your last chance to buy gold and prepper supplies before Russia presses the big button. If these headlines sound hyperbolic or biased, well, that's because they are. On either side of the political spectrum, the news is meant to sell you a narrative and usually dramatically exaggerates or misrepresents events to get clicks. This video's sponsor, Ground News, collects related articles from dozens of news outlets into one place and ranks them based on political leaning, factuality, and ownership to determine what sort of bias an article has so that you can think critically about the news you read. For example, if we click on the story of Trump talking about a tax hike, we can see how these different sites reported on it and the different language they used and the spins they've put on the story. Here we can see this one is mostly being covered by right-leaning sources, but there's also a left-leaning source reporting on it, which could balance things out. They also have a blind spot feature which shows stories that are being over or underreported by either side. Ground News is completely subscriber funded. It doesn't have any ads, which helps keeps it independent since, as you're probably aware, advertisers play a really big part in influencing what stories a news outlet does or doesn't run. Check them out using this QR code or go to ground.news/hyperspacepirate to get 40% off their Vantage plan. Okay, back to the thing. Here's what the flashback looks like when the system is powered off. The snap isn't really too loud as long as the bubbler is filled all the way up. Now that I know it works, it's time to get some more filter casings and print more plate holders and triple the capacity. The target current for each module is about 10 amps, meaning up to 30 amps at 48 volts for the full system. There's not many power supplies with that specification though, so I found it easiest to just have separate 12.5 amp supplies for each module, which would be all run off the same 110 volt cord. The nice thing about this setup is that by having each individual module on its own switch, I have some ability to adjust the gas output of the whole system. The modules each have check valves on their outputs to prevent backflow, and the outputs are joined together and piped into the bubbler, which serves as the flashback arrestor. When the modules have been running for a long time, there's a significant volume of water vapor inside of them. When they're turned off and the vapor cools and condenses, this causes a suction effect that can pull water into the module from the bubbler, so that's why the one-way valves are necessary. Here's what the output looks like with a 0.9mm nozzle. Quite a bit of power coming out of that thing. Let's see what it can melt. I'll start with some beach sand. It doesn't melt very easily when it's pure, so I tried mixing different salts into it to lower the melting point. The two most common additives are either sodium carbonate or borax. I think between the two of them, borax made it easier to melt the sand, but in both cases the result was really crumbly and brittle, and I never got it to be transparent. With a little more heat, the sand and sodium carbonate mixture actually starts to look like real glass, although it has this funny bluish-green tint to it. The best looking glass I got was actually some black obsidian from melting lava rocks. They melted pretty easily and the final product seemed to be more durable than the stuff I made from beach sand. And now here's some table salt being melted. When I was done, I ended up with a giant salt crystal. I even taste tested it and it was still pretty good. The flame actually works really well for brazing copper. The heating power is lower than that of a blowtorch, but because of the higher temperature, in a small area like a tube joint, it heats up quite a bit faster. The effect of limelight from heating the calcium in a seashell with the torch is so intense that even with welding goggles on, it's really difficult to look at. This might be an idea for a grossly over-engineered nightlight. Let's see what happens to a soda can. Those blue flashes are from the aluminum in the soda can actually igniting, because the torch gets so hot that in some cases it can strip away the oxide layer and burn up the metal underneath. Let's see what it can do to concrete. The presence of calcium oxide is pretty obvious here from the super bright limelight coming off of it. I'm not much of an artist, but this is definitely one way to draw pictures on concrete. So there's plenty of heat for cutting steel, as you can see here. Welding is a different story though. I could clearly see a molten pool when I was trying to weld the joint, but the weld is just slag and immediately breaks apart. Even with tons of flux, this still happened, and I think it's just because the flame is essentially just superheated steam, so the water is oxidizing the steel. I think it's the reaction here that's happening, and the slag is magnetite because the oxides are black and still attracted to a magnet. Red iron oxide wouldn't be attracted to a magnet. I replaced the water in the bubbler with some denatured alcohol in order to make the flame a little bit more fuel-rich by adding the alcohol vapors into the stream and hopefully avoid oxidizing the steel. The flame was noticeably larger and brighter, and I got this little blue cone at the nozzle output after the alcohol vapor was added to the stream. The weld joint was still mostly slag, with the exception of one little spot where this piece of steel actually didn't manage to stick. To make this really work right, the HHO will probably need propane injected into it. On the plus side, the torch is still really good for melting and welding borosilicate glass, which could be really handy for making your own modifications to lab glass for special applications. I was able to melt a glass stirring rod into this bead thing that has a hole for a necklace chain. Now this wouldn't be a video about HHO if I didn't blow some stuff up, so let's see some of that. This all got me wondering about the danger of these explosions, and while the detonation velocity of stoichiometrically balanced hydrogen and oxygen is over 3,000 meters per second, based on some articles I was able to dig up, it seems like the shockwave pressure is only around 20 atmospheres max. Now compare that to solid high explosives like PETN or RDX, which can produce pressures in the thousands or even tens of thousands of atmospheres, and it's not even remotely close. This is why you'll see videos of people safely detonating bubbles of HHO in their hands. Really the biggest hazard is hearing damage and a minor risk of fragmentation. And the fragmentation isn't even really that much of a hazard because I found on accidental detonations inside of closed containers that the blast cools and drops pressure before it can tear material apart and project frag outwards. Even so, I'd still strongly suggest using eye protection. In addition to that, the combustion products of HHO detonation aren't gas at room temperature since the product is just water. So if you had a closed container at 1 atmosphere full of HHO that you ignited, you'd get an overpressure of around 20 atmospheres peak. But once the resulting vapor cooled and condensed, you'd actually end up well below atmospheric pressure. This is the same effect you can see with so-called steam vacuum, where all the air in a container gets displaced by water vapor, but when that vapor cools and condenses to room temperature, the vapor pressure is below 1 atmosphere, so it causes a suction. So anyway, that's my large HHO system. It's definitely got a use as a gas welding system for when you don't want to buy oxygen and acetylene. And I think it might also have a few other niche uses, like maybe a solid state pump using electrolysis with a spark plug to create pressure waves from detonation. Now please excuse me while I use mine to get rid of this gopher tunnel network in my backyard.